Hello.
Hello guys. Hello Eric. Hello Ryan.
Hello guys.
Okay, so today we'll talk about something that very interesting is called the algorithm.
Algorithm. What is algorithm?
Algorithm complexity.
Algorithm.
Complexity.
Complexity.
Yeah. Do you know this word complexity?
Very hard, baby.
Yeah. Complexity is the
Very
It means-
hard, baby.
complex. Yeah. Complexity.
Yeah.
So why
It's hard, very
why do we need this? Because that it's a way that we analyze how efficient an algorithm is. Okay. So
algorithm.
yeah. Okay. So for example, like if I have a number, a list of number like 3, 2, 1, 5, 7. So this is the computer. This is the list to computer input. So if we want to know the maximum in this list, how what do you think? How many times the computer needs to check? Like this is the numbers. This is a list of numbers.
What are we doing?
So finding the maximum.
Maximum 7.
Yeah, I know. The human can just look, it's 7, right? But the computer don't know. He has to check the first number. Okay, he has to keep a maximum, count a maximum. For example, it's 3. Is 2 bigger than 3? No. Is 1 bigger than 3? No. Is 5 bigger than 3? Yes. Then he update this. Yes? Yeah? And is 7 bigger than 3? Yes. Bigger than 5? Yes. Okay? And then now he found that is. So the computer needs to scan once, right? If there are n items, n elements in the list, he needs to check n times. Am I right? Yeah? So you know how to do this, yeah? Define, yeah? Max n, right? Yes? Yeah, you can just do this if this answer is a very small number. Let's say put in the first number at the beginning and 0, okay? And then do for I in answer in n. What do we do? If I bigger than answer, right? Then answer equals I, am I right? You see? Checking this list, and if it's the number is bigger than the current maximum, and I update it, right? This is the method I just told you, right? Giving the maximum 3. If 5 update it and the current maximum is 5, 7 bigger than 5, update it is 7, okay? Okay, so look, the computer needs to check n items. So each time it needs the n, right? So this leads to our complexity. We use the big O, which is n. Okay, this is called linear because the computer need. If there are 100 items, yeah, if n is 100, then computer needs to check how many times?
100.
Yes, exactly. 1,000?
1,000.
Yes, you see, as this grows, and then the computer needs to check that number, yeah? So it basically, this is n, this is t, and then basically it needs to check. This is called linear, yeah? This is 100, and then what it corresponds is 100 here. Got it? This is called linear.
Yeah, baby.
Okay, so this is called linear. Okay, so how?
Linear search.
Yeah, you remember. Okay, so I put it here.
Yeah, you remember.
O
Minus research.
and this is called linear, yeah? Linear.
Linear.
So how about, let's say, if I want, remember yesterday we talked about mathematical induction, right? Remember?
Yeah.
Can you remind me for the sum of the first n positive numbers?
What do you mean?
Remember? 1, 2, 3, n. Remember?
Yeah.
Remember this equals n times n plus 1 divided by 2, right? Yes? 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 Do you get it?
Yes.
Okay, so tell me, if n is 1,000, how many times does the computer need?
1,000.
No, because the computer can just work out by this mathematical formula, right? It's just, you can just plug in the 1,000 here, right? And then you can get the equations. You can get the number immediately, right?
What?
Even it's 10 million,
It's one time.
yeah? Or one time, yeah. If it's 1 million, it's still instant, right? Computer can just work out the formula instantly. So it means that the complexity does not grow as the size of the input. So what does it mean? It's the complexity is O1. O1, which is called constant. Do you get it?
Is that O is 0?
Oh, big O. Oh, oh, like O.
Oh.
Yeah. Okay, so this is another way. Okay, constant.
Oh.
Remember the binary search.
Yeah.
Yeah.
1,
So-
3, 3.
Yes, exactly. So look.
Yes.
So tell me,
Tell me.
if they are,
Give me.
Look. if this is 0, this is 8. Okay. If this is 0, this is 8. How many times I need to, for the computer needs to check? If I want to look for the number like 7, how many times
7.
Yeah, the computer needs to find the number 7 here. And in binary search, remember? How do we do it? How do we do this binary search? Do you still remember? How do we do the binary search? We
With the
check.
binary tree.
No, we check in the middle, right?
Yeah.
The middle is 4, right?
Yeah.
Yeah, and
So
if-
what happens if it's an odd number?
It doesn't matter. You just pick the middle number. It doesn't have to be exactly the middle. It just have to be around middle. So is 7 bigger than 4?
Yes.
So it's definitely in this side, right?
Yeah.
And then and 8 and 4, the middle.
What?
4 and 8,
6.
6. Okay, so here. And is it 6, 7 bigger than 6?
Yeah.
Okay, so I don't need to consider this, yeah? So the answer is here, right? 7 and 6 middle.
7.
Yeah, we find it. You see? So how many times maximum it needs? It needs 3 times, right?
Yeah, 3 times.
3 times. So why do we know it's 3 times? It's that 2 times 2 times 2 bigger or equal than 8, right? There are only 3 2's, right?
Yeah.
Yeah. So this is called log. So you probably don't know the function yet. But
That's equal.
yeah. So we can write this way. Look, if 2 times 2 times 2 equals 8, right? Yeah. 2 to the power of 3 equals 8, am I right? Yes? Yes? So we can write it this way. 3, look this number, look, it's very, look this, yes? 3 equals log 2, 8. Got it?
Log 2, 8.
This is log function. So basically, look, log AB equals C. What can we get?
Log
A to the power of C equals B. Okay, this is you basically can transform to each other. Okay, do you understand? So 2 to the power of 3 equals A. So we can write 3 equals log 2A. Okay, so log 2 is a function. It takes the n x. Y equals log 2x. So we can transform 2 to the power of x equals y. Got it? So the complexity for this is O log n, right? We call it logarithm. Okay, I don't know how to spell this. Logarithm, okay? Logarithm. So basically it's for the binary search. If the size is 16, how many times the computer needs?
Do you mean about
Yeah, if this binary is 16, how many times does the computer need?
3?
No, 3 is 8.
16. 4.
4, yes, because it's one more step, yeah?
Yeah.
Yeah, 128. It's getting harder, yeah?
Wait. 5, 6, 7. No, 8.
8, yes, 8.
Oh, yeah,
Look,
that.
128 equals
Oh, yeah, that.
log. So we get basically log 2. This is equals A, right? We can write it this way: log 2 128 equals A. So basically, it's 2 to the power of A equals 128. Okay. Okay. So this is log n. Okay. So now moving next, as you can see, this is the most efficient. Yeah. I should probably write it this first. Constant is the most efficient, right? And then on linear. But no, and then log n faster than the O n. And then what's next?
Nothing. Yeah.
N square. We call it n square or quadratic. Okay, how do you?
Korean.
Quadratic. How do you spell it? Quadratic. Yeah, quadratic.
Quadratic.
Do you understand this word? Quadratic. Yeah, it basically means this. You got a square, right?
Well,
Eric. So
yes.
look, Eric. Look.
Yeah.
If there are 5 numbers.
Yes.
Yeah.
5 numbers.
5 numbers. 1, 2, 3, 4, 5.
5, 6, 7, 8, and 9, 10, 11.
So can you tell me how many pairs can
15,
if you pick
30.
2 numbers from it, how many pairs can you do it? If there's you know, sequence, like you can pick 1, 2, you can pick 1, 2, right?
Yeah.
Maybe 3, just 3 numbers, yeah? 1, 2, 1, 3, 2, 3, right?
Yeah.
And then you can do the other way, 2, 1, 3, 1, 3, 2, right? So 6, right?
Yeah. Whoa. You can just times it by 2.
Uh,
You can just times the top number by 2.
yeah. Okay.
See?
Okay, actually,
We are better.
yeah. So look, so how many how many solutions will that be?
What?
How many? So if I pick n here, right? So I need to go through n minus 1, right? N minus 1. So basically the solution is left, right?
Yes.
Divide it, do we need to divide it? 3 times 2, 6, right? Yeah, 3 times, yeah, that's
1,
it.
2, 2, 1, 3.
Yeah. If you want the always the smaller to the biggest one, if you 1, 2 and 2, 1 is the same, then you probably need to divide it by 2, right? So, okay, Eric. So we haven't talked about another one. Is called
Binary search.
no. This look linear search, yeah.
Yeah.
I just put it here for a while. This is n square, right? N square. Like this is called quadratic.
Quadratic.
So
Not quadratic.
okay.
It's quadratic.
So Eric, so how about if a list, yeah, there are n items. If I want to search only half of it, so this algorithm, if I told you I want to just to do half of it, what's the complexity? Is it still linear?
Linear search. Binary search.
Yeah?
Cuckoo
Is it
search.
still linear?
Yeah. Reverse search.
Look, there are n items, but I only need to scan half of it, right? Previously it's linear, yeah, because but this time the t is 2n to the over of 2, right? But still it's on. The complexity is on. Why? Because we drop the constant. If it's constant, we drop it. Yeah? Because the constant don't change. Am I right?
Yeah.
So for the algorithm analysis, if there's a constant, if even it's 2 times n, 100 times n, yeah, if it needs to go through 100 times this approach, it still counted as
Ow.
linear, right?
Sorry.
Am I right? Okay. So the quadratic is let's go back to the quadratic, okay? We haven't talked about that. Quadratic.
Quadratic.
So
When did this done?
yeah, almost. Quadratic, remember, we talked about the sorting algorithm, right? Remember? Yeah? Don't touch it, okay? Look, Eric, 3 numbers. 3, 4, 2. If you want to sort it.
2, 3, 4.
Yes, I know, but computer, look, computer, if the n is 3, yeah? And 3 numbers, how do we solve it? Computer here. And then another, this is I, this is J. Yeah?
Upside down.
The 2, okay, compare, right? And then compare. If 2 is smaller than 3, okay, I swap it. Okay? And then J is here, yeah? If 3 is smaller than 4, and then swap it. So basically, if the I needs to go through n step, right? And for every I, the J needs to go through n minus 1, n minus 2 step, right? And etc. So the complexity is the checking is around n times n minus 1 divided by 2, okay? So this is still quadratic, am I right? Look,
Quadratic.
because this is a constant, am I right?
Yeah.
Eric, this is constant, this is constant. So this timing is still approximately to quadratic. Okay, so we all so when the algorithm gets more complex, we also have these. Yeah, we call it cubic, right?
Cubic.
And we have something in between here. Yeah, we call it O(n) log n. In the future, we come. Audience will not see. In the future, we come across some quick sort. Okay, maybe I talk about the quick sorting algorithm tomorrow. And so look, O1 constant is the most efficient. Yeah, if you can solve a problem using O1, we prefer the O1, right? And then this is the second logarithm. Yeah, logarithm. And then quadratic, and linear.
Yay!
Linear, and this one, and quadratic and cubic. And then we have also the exponential 2 to the power of n.
Yeah.
And we also have n factorial, remember? Factorial. Yes? Oh, we also have O square n.
How about
What's
fun?
this?
Square root.
Square root. Remember, we want to check if a number. We want to check if a number is a prime number or not, right? We only need to go through the square root of integer to check if it's divided by that, right? Divisible. And yeah. So
GG, come to the conquerors. GG.
can you give me an example of the factorial? Remember. So if this 1, 2, 3, okay, 1, 2, 3. So that you want to know how many ways I can list those three numbers. How many? 1, 2, 3. How many ways I can list three numbers? 1, 2, 3. 1, 3, 2. Right? 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1.
18.
What 18? Only 6, right? Is there only 6? Can you list any other more permutation? We call it permutation. Permutation, yeah? Permutation of n items is n factorial. Do you understand why? If there are n numbers, how do we know it's n factorial? How many ways? These three numbers, 3 factorial equals 6. So there are 6 solutions. Do you know why? Okay, if I put n numbers, how many solutions I can put on the first integer, first bit? I can pick how many solutions? How many?
5.
Why is 5? There are only three slots.
6.
No, what I'm checking is how many there are 3 numbers. How many numbers can I put in the first one?
Do a fraction. 1.
Why is 1? There are 1, 2, 3. Why is 1? How many numbers I can put on the first slot?
2.
I just told you 1, 2, 3. How many more numbers can I put?
3.
Yeah, 3. Yeah, I can put 1, 2, 3. Yeah, the first one. Yeah. If I pick one numbers, how many numbers can I put in the second place?
2.
Yeah, because I already put 1, right?
Yeah.
Okay, 2. And how many numbers I can put for
1.
You see? So if there are n numbers, I can do it this way. n times n minus 1 times, look, n minus 2, right? And until 1. So this is exactly the n factorial. Do you get it? So if I tell you, if the 4 numbers, 1, 2, 3, 4, how many permutations are there?
24.
Yes, exactly. Do you get it? So this is called factorial, right?
I know the
Yes,
factorial.
Okay, so
I know how to draw one. Factorial begin with an F, and then a right angle here,
yeah.
and then you put whatever number here. I choose 1, and then 2, and then what about the right angle?
Okay. Okay, so let's do the sorting now for this sorting. Okay, so look, this is the first one, yeah? First, the fastest. Sorted from the fastest to slowest. Constant is the fastest. And then log n second. Square root third. Linear fourth.
Factorial 5.
And egg log n 5. And then what's next? Quadratic 6. Cubic 7. Right? And these two, which one is first? I don't know, I have to check. Maybe this is next and this is, yeah, this is the slowest. Okay? Do you get it?
What the fast is? Oh yeah, contact.
Yeah, constant. Do you get it?
Constant.
So to sum up, if we design the algorithm, we need to analyze the complexity, okay? Right? And another way, this is called runtime complexity, and also we have another similar approach, similar analysis called space complexity. Space is, we can also use these to analyze the space. It means how many space do you need, right? If you need another n items, if the size is n and you need to allocate another n space for this algorithm, then the complexity is O(n), right? For the space. Got it? Yes? Okay. Good job today. Any questions?
No.
Okay.
What do you say, Papa? Papa, oh yeah, up there.
No shaking. What did I just tell you?
Yeah.